Hey guys, it's Mr. Ray here with our next calculus lesson. We are finishing off the curve sketching unit tonight, or today. Um, so today's lesson, we're just basically putting all the pieces together and we're coming up with a new revised calculus course algorithm for curve sketching. Um, so this is pretty much out of the textbook um, in terms of these steps. The steps don't have to be done in a specific order. There's some things that obviously will need to be done before other things, but really this is just kind of a checklist to make sure you cover all of these things. Once you do each step will provide you with a piece of information, and once we get to the end, you can see the last step is to complete the sketch with the above information. So very similar to what we did in polynomial sketching in advanced functions, but there's a couple of new things here. The first thing is, well, if we just go down through this quickly, determine any discontinuities or limitations in the domain. If there is a discontinuity, investigate the function's value on either side, see what's going on at that place. So that could be, it could be a vertical asymptote, it could be a hole, could be a spike, but most of the time it's going to be a vertical asymptote or a hole. And then determine any vertical asymptotes, that comes directly from here. Determine any x or y intercepts. So we didn't do much of this in terms of the review, but now we're going to be finding those things. And then this is basically lesson 2. Determine any critical numbers by finding where the derivative is equal to 0 or where it's undefined. And then based on that, determine using interval testing, find where it's increasing, decreasing around these critical points, and test these points to see if they're local max, mins, or neither. Okay, so this can be done as we learned in the last lesson. You could actually do what we did in lesson 2 with the intervals. You could see if it's increasing, decreasing on either side and make a conclusion that it's a max or a min or neither. Or you could do the second derivative test, which we're going to do the second derivative test in our second example, or maybe it's the first one. Yeah, first one, to determine whether it's a local min or a max. Okay, and that doesn't always work, so it's a bit of a risk. Okay, so this one here, number 6, that's basically the end behavior of the function. What's going on at the ends. That will identify horizontal asymptotes if they exist. At the same time, I'm not sure why they separated this so much. It could be 6, this could be 6a, or this could be 6b, because you could have a horizontal asymptote or an oblique asymptote, depending on your equation. So it could be this, or it could be this, or it could be neither. Okay, so these two probably should go together. And then this number 7 here, this is basically last lesson. Determine the second derivative and test for points of inflection using the intervals of concavity. Okay, and then once you've done that, you've gathered a whole ton of information and you complete the sketch. Okay, and a quick note here, you will not use all the steps in every situation. Use only the steps that are essential. You're familiar with the basic shapes of many functions. So a lot of knowledge from advanced function will come through in this. Use this when you can. Okay, so we're just going to do 2 examples today. The first one here, now I apologize for where the page breaks. Basically, there's only like a third of a page here and then a blank page. I got to change where my page break is. So I'm going to put that at the top and then just kind of do the work on the next page. Maybe I'll fold this over just so you can see the whole thing at the same time. Okay, and then we'll do the second example on the other page. Okay, so here we have Use the algorithm for curve sketching to sketch the graph of f of x equals this. You can see this is a polynomial, and we're going to use our knowledge of polynomials a bit here as well. So the first thing I look at is, because it's a polynomial, basically the domain is x can be any real number, so there's therefore no discontinuities. Love that word. And we can say because it's a polynomial if you want, but you don't have to. Let's go do the x and y intercepts. So basically when you're doing this, you're going to have a great deal of calculations here. So it's important to just keep it organized for yourself and for your teacher, so we can find so I can find what you're doing and if it makes sense or if you left something out. So if I want the y-intercept, don't forget that means you set x equal to 0. And when you've got a polynomial function, that's really easy because, you know, that's 0, that's 0, that's 0. So basically the y-intercept is 0. Okay, so there's our first real piece of information for the graph. You do the x-intercepts. Now the x-intercept, you set y equals 0. Okay, now it's not quite as easy as the y-intercept. So you set that cubic equal to 0. And the idea would be to factor it, or use, at some point, if you could use the quadratic equation to find the zeros. Things that you learned in advanced functions to find zeros of higher degree polynomials. Hopefully you won't be getting any of those. I mean, there's enough work to do here already. I don't need you trying to find all the zeros of a 5th degree polynomial. That's cruel and unusual punishment, so I won't be doing that. So if I notice here, I can factor out an x, because every term has an x, and in fact, I'm going to factor out a negative x, so that the rest is basically a positive a value here, 3x squared minus 2x. So that's a plus 2x minus 5. Okay, and I'm going to leave out some steps here. Obviously, it might take a bit of work to factor that for some people, or maybe not. Now this does factor to 3x plus 5 and x minus 1. So if you were doing that factoring work, I don't really want to see it. So you do that on a separate page and just tell me the final factored form here. And from this, you can get your x-intercepts. X-intercepts, so don't forget about this. That means there's an x-intercept at 0. And here that would be negative 5/3. And this would be 1. So there's 3 x-intercepts. And one thing, in case maybe you've never seen this before, if you get a y-intercept at 0, that means there's a point on the graph at 0, 0. So a y-intercept of 0 also means an x-intercept of 0. So those two always go hand in hand. So make sure you've got both. Okay, you can't have an x-intercept of 0 without a y-intercept of 0 and vice versa. Okay, so we've got the x and y-intercepts in that stage. So the next thing we should do is look at the critical points. Now this numbering system is my own. I'm not necessarily going by the steps in the algorithm. You can do, I'm just showing you the order I'm doing it. So if I go down here and jump up here and then maybe go down here, that you see make sense of what's going on. So critical points, we want to find the derivative of f of x, and since it's a polynomial, that's fairly straightforward. So that's negative 9x squared minus 4x plus 5. Okay, and then to find the critical points, you set that to 0. Now I'm going to factor out a negative 1. When you factor out any constant, it doesn't affect the zeros at all. So I'm going to do that right now. So that would flip the signs of all the terms. And again, I'm doing that just so it's easier to factor. Some people can factor that in their heads. I prefer to have the a value positive if possible. And when we factor that, we get 9x minus 5 and x plus 1. And that means we have critical points at x equals 5/9 and -1. Now, for the point of the graphing, it's not a horrible idea if you round to the nearest decimal, like tenth position. And I'm going to be doing that in a few cases because some of the answers are pretty hairy. So I've got these two critical points. X equals both of those. We don't know whether they're local mins, local maxes, or neither at this point. Now, you could do the interval testing here, and that's definitely a fine option. I'm going to actually do the second derivative test to find these, and I'm actually doing it because it works, and it's actually less work if it does work. If it doesn't work, you basically have to go back and do the other method anyways. So what I'm going to do here is I'm going to skip down to the next step for now, where I find the second derivative. So I'm looking at, well, let's just call it points of inflection, possible points of inflection. So this is where you look at your second derivative. So that's the first thing I have to do. What is the second derivative? You just take the derivative of the first derivative, so that's negative 18x minus 4. And if I set that equal to 0, this is just a linear, so this works out to x equals negative 4/18, which is negative 2/9. Okay. Now what I would like to have is, when I have these important points, that I have the x and the y coordinates. So what we would do here is plug that value, negative 2/9, back into the original equation, the cubic, and find that you have a y value at negative 1.17. So negative 2/9, negative 1.17. Okay, we're still not sure if this is a point of inflection yet. We're going to be doing some interval testing for the second derivative, the concavity. We're going to do that over here. But before I do that, I'm now going to do this second derivative test. Second derivative test for these critical points to see if they are local mins, local maxes, or neither. Okay, so when I do that, I get, so the way I do it, f double quote, or the second derivative at 5/9. Okay, now all we care about is this a positive, negative, or 0 answer. So you don't have to be precise here, you just have to know the correct sign. And in this case, it is negative. So I'll just put a negative sign in brackets. And if I do the same thing, second derivative at negative 1, that result is going to be positive. Okay, so when it's a negative value, that means we have a local max at this point, so 5/9. And then you would, I'm not going to do that here, but you'd plug your 5/9 back into your f of x and find out the y value, which is about 1.6. And again, this is where we're kind of coming up with an approximation, because it's really just for the point of the graph. We're not going to be overly accurate because that's pretty precise already. So that's a local max at that point. And since this second derivative is positive, that means that point is a local min because the second derivative is positive, and that's at the point -1, and this one actually works out to -4. So that's 100% accurate. Okay, so we've now got local min, local max, a couple of 3 x-intercepts, a y-intercept. Let's keep going. So based on this point of inflection, what I'd like to do is do interval test. Well, we'll call it concavity or concavity testing maybe. You can use whatever terminology you like. So I'll move this up a little bit. Okay, so basically the only point I'm really testing, if there was a discontinuity, I would include that value as well as the point of inflection. But since this is a polynomial, that's the only real point of concern. So I'm going to make my table here. I'm going to have interval. I'm going to have second derivative, and here I'm just looking for the sign of the second derivative and then what the graph looks like. So fairly straightforward. And so I'm going to actually have 3 columns here. So I'm going to have x equals -2/9, x is greater than -2/9, and x is less than -2/9. Okay, so this is the point we think is possibly a point of inflection, but we want to test the concavity to the left and to the right of that point. So now when I do my interval testing, basically what I'm doing is I pick a test value for each of these intervals. This isn't really an interval, that's the border. So -2/9, lots of options. -1 might be a good value for that, and here 0 would be fantastic. So when I plug that into the second derivative, I'm just looking for the sign. So I plug that back into here. 0, you can tell already. Well, let's just do the test here. So if I plug -1 in to the interval test, I actually get a positive value here. Obviously, when I plug -2/9 in, well, we already know that value is 0 from our previous section here. And when I plug 0 in, which is that interval, test value for that interval, I get a negative. Okay, so positive value means concave up, negative value means concave down. And what would this look like? Well, this would be starting up there and going up so that these two can actually connect. So it basically starts with this side and connects to this side. Okay. The only other thing, like there was no need to look for vertical asymptotes, but there's also no horizontal asymptotes for polynomials. So one thing we could do though is look at the end behavior. We don't absolutely have to do this, but it's always a good check because sometimes some weird things can happen or mistakes are made, and this is a good sanity check. Okay, so all this has to do with is, the sign, the degree of the polynomial, which is degree 3. So it's an odd degree polynomial, and it has a, if I remember correctly, it has a negative leading coefficient. So that means the end behavior looks like this. Starts in the second quadrant, ends in the fourth. Okay, so at this point now we're ready to do our fairly accurate sketch. Now if you're doing this on an assignment, I would like you to use either a grid or a ruler. Okay, so I'm going to make my grid Now, when you're making your grid, obviously it's important to look at the points that you have that are x-intercepts, y-intercepts, local mins, maxes, points of inflection. Make sure that you've made your grid in an appropriate scale so that you can actually see them and you don't have to redraw it. Okay, so first thing I'll do is put my intercepts. So I have an x and y intercept there. I've also got 1 at 1, x-intercept at 1, and negative 5/3 would be about there. Okay. Now I've also got, if I go back to my critical points, I've got a local max at 5/9 and 1.6. So that's about here. You can see why it's important to get the y coordinates, because just knowing the x coordinate of your max or min doesn't really tell you how high it goes. Okay, so the y value, the y coordinate of these critical points, extremely important to put for your graph. You know, I could have guessed it's up here, but knowing it's there makes the graph much more accurate. Okay, and then the other local min is, or the only local min is at -4, -1, -4. Okay, and I could put my point of inflection, -2/9. Now, I guess I didn't actually finish that off correctly. So, where are we? Oh, I did. So I got my x and y coordinates here. That's fine. So -2/9. That's about there, and -1.17 is about here. Okay, so that's the point of inflection. Okay, and in terms of behavior, just so I'll put my rough arrows there. So I know that I'm coming down from here. I reach, so I'll put a little cup here because that's a local min, that's a local max. Okay, this is a point of inflection. So I know from here to here, all the way up to here, that's concave up. But as soon as I hit that point of inflection, it becomes concave down. So it basically changes to this. And then it's concave down all the way, and this is concave up all the way. Okay, so that's a pretty accurate. This doesn't look all that smooth, but I mean you can get the idea. That's where the concavity changes. So concave down and then concave up. Okay, so as long as you get the idea what the point of inflection is, that's good. So this would be a very good example of a polynomial, curve sketching a polynomial based on all those things we learned in advanced functions, plus the things we've learned in this unit with first and second derivatives, critical points, points of inflection, concavity. Okay? All right. Now you can tell that each of these questions takes a fair bit of time. When I get you an assignment, typically on a test, I give you 1 or 2 of these plus maybe some partial calculations. Like I might give you an equation and say, you know, find the critical points and are they local mins, maxes, or neither? Or maybe I say, what are there any points of inflection on this equation? Just so I can see if you're doing each of the steps from this unit correctly. I'm not going to give you a question to find the x and y intercepts. That's not what I'm really testing you on, although you still have to be able to do it in the big question. Okay, so that was the first question. Second question is a rational function. Of course, we have to throw one in. Okay, let's get organized here. Okay, use the algorithm for curve sketching to sketch the graph of f of x equals x minus 4 equals x squared minus x minus 2. First thing we're going to do is factor if we can, and most of the time you can. So x minus 4 on the top, x minus 2, x plus 1 on the bottom. Okay, and we're going to be using the factored version not only to find the vertical asymptotes or holes, but also for positive, negative results, things like that. Okay, so first thing we'll do is look at the intercepts. And the y-intercept, that's when you set x equal to 0. Okay, so when I set zeros here, I get negative 4, negative 2 times 1, so negative 4 over negative 2, that is y equals 1. Sorry, y equals 2, so that's your y-intercept. Okay, your x-intercept is when you set y equals 0. Okay, now I'm not going to do the whole thing here, but basically when you set y equals 0, you're setting this whole thing to 0, which means you're really solving for the numerator equals 0. So in this case, x would be equal to 4. So there's your x-intercept. You only have one of those. And of course, you never have more than one y-intercept. Okay, so now that we're talking about rational functions, we've already talked about asymptotes. Let's do the vertical asymptotes. So these should be fairly straightforward to get. You set each of these denominator factors equal to 0, and you get x equals 2 and x equals negative 1. Okay. Now, if we look at the degree of this rational equation, we have degree 1 on the top, degree 2 on the bottom. That means you're going to have a horizontal asymptote, and because the degree is because the degree is higher on the bottom than the top, that means that horizontal asymptote is always y equals 0. Okay, so we got those pretty quickly. Now, from the horizontal asymptote, I want to look at the behavior, basically the end behavior. Now let's just call it behavior. So how is this, not so much as it going off to positive infinity or negative. Since there is a horizontal asymptote, we know it's at the end it's headed towards y equals 0, the x-axis. We want to know is it coming from above or below. Okay, so there's a variety of ways of doing this. The way I discussed it earlier, we just plug in 100 and negative 100, and in this case, since it's y equals 0, we can just find the sign. So f of 100 is positive, f of negative 100 is negative. So that basically means as x approaches positive infinity, y approaches 0 from above. As x approaches negative infinity, y approaches 0 from below. Okay, so got those. All right, so let's jump into the critical points. I'm going to make sure we leave room for our graph at the bottom, so don't use your space wisely. So here we have critical points. So this is where we take the derivative of the function, and I'm not going to do every step here. This would also be where you would calculate the derivative, because you probably use the quotient rule. You could use product rule possibly, but I'm just going to show the end result here, and that end result is negative x squared plus 8x minus 6 over x squared minus x minus 2 squared, all squared. Okay, so when I set that to 0, remember I'm really just looking at the top. That has to be 0 for the whole thing to be 0. So I'll just leave it like that. Now actually I'll do what I did before. I'll factor out the -1 so it's easier to factor. X squared plus 8x. Sorry, that's a minus 8x. And then plus 6. Now, unfortunately, this does not factor, so you'd have to use quadratic formula. And when you do that, you get x is equal to 4 plus or minus root 10. So two critical points. And when you look at each of these points, so the first point will be 4 plus root 10, that's about 7.2. And this one would be 0.8. Okay, now did I figure those out? I did. Hard to read my writing here. So I think that's a 0.1, and this is I think it's a 6.5. Anyways, it's all you're doing here is plugging these x values back into this equation. Now, we don't know that these are local mins, local maxes, or neither. So what we're going to do to the side here, see if I can squeeze this in. Actually, I'm gonna take a bit more room so you can read this. Now, when I do this interval test, okay, of course I'm going to be using 7.2 and 0.8, but I'm also going to be putting in my vertical asymptotes because that's where the function's discontinuous. And you notice when I did the vertical asymptote, horizontal asymptote, I didn't do the vertical asymptote behavior. So you could do it there and not do it here, or you could do the two things together. So I'll show you what I mean by that. So basically my intervals, let me break this into parts. Got 1, 2, 3, 4, 5. Okay, so lots of intervals. And I'm going to show the first derivative, the sine of it, and then basically the graph of f of x. Okay, so if you notice here, I've got, we have to put these in the right order, ascending order. I've got 7.2, 0.8. I've also got -1 and 2. So my first interval will be from -infinity to -1. And I'm going to put round brackets because at -1 I've got a vertical asymptote. And then I start from 1 and I'm going to go up to the next, so that's -1. From -1 to the next one, which is 0.8. So 0.8 is a critical point. And then from 0.8, I'm going up to the next value, which is 2. So the interval from 0.8 to 2. And then the interval from 2 to 7.2. Okay, so you can see where these breaks are. I've got a break here at 2. I've got a break at 0.8, -1. So these are either my discontinuities or my critical points. I'm actually putting them all together. And then this last one is 7.2. The last interval goes from 7.2 to positive infinity. Okay, so we already know it's, at -1 and 2. It's not continuous at these points. and we'll show that. Okay, so if I plug in a test value, so could pick anything, -2. If I plug in -2 into the first derivative, I'm going to get something that's negative. If I plug, say, I guess I could plug 0 in here into the first derivative, I also get a negative value. If I plug, say, x equals 1, which is a test value in between here, I'm going to get something positive. And this interval, I also get something positive, and this interval, I get something negative. If I plug in 8 or 10 or something. Okay. Now, all I'm going to do here is whether it's increasing or decreasing, and that's already told me decreasing, decreasing, increasing, increasing, decreasing. So sometimes it helps to get a visual perspective of what that means. Okay. So that's what those mean. That's a very direct interpretation of those signs. Okay, so what do these points mean? Well, we already know that this is a vertical asymptote. And what I was saying about the vertical asymptote behavior, we know that the function is decreasing to the left of this vertical asymptote and also decreasing to the left as well. Okay, we can use that instead of our vertical asymptote behavior. Or, like I said earlier, you could do that and just do the critical points, but this is an option. Okay, this point here, this was a critical point at point 8, and from the behavior on the left and right, we know that this is a local min. Okay, and yeah, so that's, we got the point there, point 8, point 1. We'll just put it in again. Now, between here and here, we know that's also a vertical asymptote at x equals 2. And at this point, 7.2, we can see that has to be a local max. And that's at 7.2, I believe. Oh, no, that must be wrong. 7.2, I think that's, no, I can't even tell my own writing here. I think it's 0.5. Okay, so we've got all that. Now, the only thing we're missing here that we don't have is the points of inflection. Okay, if I did that, what do we have 2 here twice? That's a 3, so 4. So if I do points of inflection, so if you did the second derivative, this is where it gets pretty hairy looking. So you can already tell the first derivative is pretty intense. If I did a derivative of that, I'll actually put the final result. You get this, 2 times x cubed minus 12x squared plus 18x minus 14 all over x squared minus x minus 2 to the power 4. Okay, so if we're to find the points of inflection, you would be setting this equal to 0. You could ignore the 2 there. So you're basically solving for 0 equals x cubed minus 12x squared plus 18x minus 14. And this only has one solution. Lots of imaginary roots. Basically, I think you can get one factor out of this, and the quadratic that's left has no real roots. Just trying to find where that value is. Yeah, it's at, no, hold on one second. Okay, sorry about that. So there is one solution for this, and that's x is approximately equal to 10.4. That's a lot of work to just get that. In fact, usually when I teach this, I don't even bother with this point of inflection. But you'll see when we do the sketch here. Okay, so let's see the scale here. I've got to go 1, 2, 3, 4, 5. Okay, so I start putting in my information. I've got y-intercept at 2, x-intercept at 4. I've got a vertical asymptote at x equals -1. I've got another vertical asymptote at x equals 2. And then I've got my horizontal asymptote at y equals 0. So it's always hard to show that. Okay. Now, for my end behavior, I know that, I'll do this one first. So from the left, I'm coming from below. So I can put a little arrow there to help me out. And as x approaches positive, it's coming from above. So something like this. Okay, so I've got that. Critical points, I've got 7.2. 1, 2, 3, 4, 5, 6, 7. 7.2. So about right there. And then, so that's yeah, we decided the 7.2 is a local max, which seems pretty low for a max, but it is. And a local min at 0.8, 0.1. Sorry, that wasn't 0.1. That was 1.5. 0.8, 1.5. So that's 0.8 and 1.5 here. Okay, so that's a local min, that's a local max. I actually have my point of inflection. Let me just make this a little bit longer so I can show that point. So that's 7, 8, 9, 10, 11. So at 10.4. Now 10.4, let's bring this in later. Now from the interval table here at -1, you can see I'm decreasing to the left and the right of -1.1. So that means coming down here and also coming down on this side as well. So at both sides it's approaching negative infinity. This one here, you can see it's the opposite. I'm approaching, no, this one is going up. This one's increasing to the right. That's what that means. And it's also increasing on the left side. So I've got that arrow. Actually, this one was wrong. So on the left, I'm decreasing, but I'm also, that would actually be increasing if I did that. This is decreasing here. Okay, so I've got my vertical asymptote behavior, my end behavior, which I erased. I've got my x and y intercepts, my vertical asymptotes, horizontal asymptote, point of inflection. So if I start doing this, it always makes sense to do each section at a time. So on this section, this seems to make sense that these two could join up. Okay, so I'll just, now we don't know exactly from our data how tight that curve is. That's probably a pretty good estimate. And then this middle section here looks like a parabola. We know this is the this is the min. So I probably have another point here. These are probably a little exaggerated. Let me move this up so you can see the whole thing. Okay, so basically I have like a cup here going up on both sides. Okay, and then this is the interesting part of the graph, because I've got my arrow down here for my vertical asymptote. So going up here, that makes sense. Although I am crossing the horizontal asymptote, but that is permitted. And I've got this over here, which kind of makes sense with that crossing. And then I have this this point here where we inflect. So basically, I can at least do that part, and then it's probably coming in more of a flatter angle. So it turns and it goes up to there, and then it comes back down. Actually, no, that's not quite right. The point of inflection. So it goes up, and this is where it inflects from concave up to concave down, and then flattens out towards the horizontal asymptote. So this is one of those strange graphs. You may remember them from advanced functions, where normally it's verboten to cross any asymptote, but it is possible to cross horizontal asymptote. So you can see that as we head off to the sunset on this side, it's still approaching 0, y equals 0, but it's never going to touch. So it is still a horizontal asymptote for sure, but it does cross over from one side to the other. And the fact that we had an x-intercept right on the horizontal asymptote was probably a good indication that something strange is going on here. Okay, so apologize for how long that took and for my confusion in some cases there. But you can see it's pretty involved. This point of inflection here, I wouldn't expect you, sorry, let me show you that. Calculating this point of inflection, I mean, all that really gave us was that point there where it changed concavity. I mean, you could probably still do a really good graph without having that, but I mean, by definition from the algorithm, it says we should do that, but I just know how much work it is to even come up with this second derivative, and then how much more work it is to actually solve this equation and get one value that really doesn't give you a whole lot in the sketch. But if you're being complete, that would be something that you should do, but I honestly wouldn't expect you to do. Okay? Okay, so that's it for this unit. Got some questions here at the bottom. Suggest that you try a few of them to get the hang of it. Again, when you're doing this, it's important to be well organized in your answer. Show me the important information you're gathering. Show me what each step you're doing. The order, it's not essential, but it kind of tells me what you were thinking as you did this. And then be as accurate as you can in your graph. Like I said before, when you do this for your assignment, please either do a nice graph with a ruler, or even better, have a grid that you can hand in or scan. Okay, so that's it for this unit. I'll be giving you your assignment on Friday. I'll try to get it out in the morning maybe this time, give you some extra time. Still have the bonus if you get it in early, due Sunday night. And then the only thing left now is the application section on optimizing using derivatives. It's kind of a cool section. So I'm going to give you 2 lessons next week, probably no assignment, and then the following week 1 or 2 lessons with an assignment, and that'll be it for the course. Okay, so hope you guys understood what I was doing here, and Have a good weekend and good luck with the assignment.